Don't scare me like that. All right. Without further ado, I want to introduce you to Paris. Paris is here. He was supposed to give the talk together with Georges, but Georges could not make it. Paris is going to tell us about the 3DS, but I know that he also has knowledge of the Nintendo 64, so make sure to ask him any questions about that as well. Did I forget anything, Paris?
No, that's all, I think.
All right, then please take it away.
All right, hello everyone. Welcome to our talk on the Panda3DS. We'll cover a variety of topics, but first I'll introduce the three names on this list. First is George. He is the creator of Panda3DS and this presentation. Next, me, Paris. I'm a contributor in Panda3DS. And we also have David, who helped a lot with making the presentation really pretty. You don't want to see the original version. For questions, you can ask either after the talk or on the Panda3DS Discord server. And lastly, you can send an email. You can send an email to these two to punish them for not showing up here. So, what is Panda3DS? Panda3DS is a Nintendo 3DS emulator for Windows, macOS, Linux, and Android. Just like all emulator projects, we have several goals and aspirations, such as providing users with a pleasant experience, creating a portable code base, exploring new possibilities, researching the 3DS, expanding the Red Panda cult, aiding homebrew developers in their 3DS software, and fun usually. Here's a peek at Panda3DS. We have three front ends, the STL one, the Qt one, and we also have an Android version. Let's take a look at what we're going to be discussing today. So, three topics. First, we're going to go over the hardware architecture of the 3DS. Next, we're going to talk about the 3DS software stack. That means the Horizon operating system and the userland. Finally, we're going to go over emulating the 3DS. We're going to talk about the levels of emulation, points of interest for new developers of the 3DS, etc. So this is a first glance at the 3DS hardware. Most of the action happens in this big chip named the CTR, which is where Citra's name comes from. It has three CPUs. So one is this ARM11 right here, and this is what runs all 3DS code. It also has this ARM9, which is the same model that was used in the DS and the DSi. And next is this ARM7 CPU, which is the same in the DS and DSi, and also in the Game Boy Advance. We're going to see why it has three CPUs in a second. But first, there's also the DSP, the digital signal processor for audio. And then there is the Pika 200 GPU, which uploads to two displays right there. One notable thing about the top display is that, as you can see, there's 2 frames here. And that is because it would generate 2 frames, one for each eye, to sort of create this fake 3D effect. It has some other miscellaneous hardware. It has 128 megabytes of RAM in the original version. In the new one, it has 256, and some other miscellaneous stuff. We're going to go over all of that. But first, the reason that it had 3 CPUs is because actually the 3DS can run DS and GBA games natively. And a fun fact about this is that many people didn't know that the 3DS can run GBA games natively, because only those who were part of Nintendo's Ambassador program could use this feature officially. And that program is something that Nintendo launched for people that bought the 3DS at the original price of $250 before it dropped to $170. Nowadays there's an open source interface for running GBA games called OpenAGB Firm. All right. So inside the system on chip, first there is the ARM11, and in the original 3DS it is composed of 2 cores running at 268 megahertz. That first core is not supposed to look like that, but let's ignore it. In the new 3DS there is 4 cores running at 804 megahertz. And we're going to see exactly what each core does, but first let's look inside one of these cores. Okay, of course my clicking doesn't work, so I'm going to manually go to a different slide. This was supposed to be a cool transition, but it didn't work. All right. Inside the ARM11 core, there is the ARMv6 architecture, and it is composed of 3 instruction sets. There is the ARM, the 32-bit main instruction set. That is what most game code is. There is the thumb. This is a reduced 16-bit version of the ARM instruction set for improved code density. Some operating system code uses thumb. And then there is Giselle, which is a Java bytecode runner in hardware, essentially. games don't use this. Some homebrew uses this. There is also a vector floating point unit. There is media instructions for video and audio decoding, say your cutscenes, stuff like that. There is an MMU for running multitasking operating systems, and I guess more stuff. And there is a branch predictor out of order completion. All right, now I will transition back to my normal slide. All right, let's pretend everything worked. There is the ARM9, which is the same as we said that was in the DS, and it has the ARM v5 architecture. In 3DS mode, it's actually used, however, to manage storage and cryptography hardware. So it's not completely unusable in the 3DS. It runs part of the operating system. We're going to look into that. And then there is the ARM7, which is for DS and GBA backwards compatibility, and it is completely disabled in 3DS mode. How do the cores communicate with each other? Well, in the ARM11, they use shared memory and interrupts to communicate with each other, and a bus. The ARM11 with the ARM9 communicates with this thing called the PXI FIFO. PXI stands for Processor Exchange Interface. I mean, there's debate. Some people say Processor Interconnect. Some people say PXI, as in fairy. I don't know. Then the ARM9 communicates with the ARM7 using the IPC FIFO. That was what it was called in the DS. So it's the same there. And now we're quickly talking about the Pika 200, which is Nintendo's first off-the-shelf GPU in a handheld, and what was used in the 3DS. It implements OpenGL ES 1.1, although most games didn't use OpenGL. And it has, some extensions, and some of those include per fragment lighting, which means it can calculate lighting per fragment instead of per vertex, hardware saddle mapping, polygon subdivision through the use of geometry shaders, subsurface scattering, which is the scattering of light as it penetrates a translucent object, and more, many, many more. And games communicate with the GPU using a piece of shared memory, which is used to store GPU commands and some other interrupt info. If a game wants to render, it first needs to write to the Pika's external registers, which configure the frame buffer and some other secondary things. And then they need to initialize the rendering context, which is done by configuring the internal registers. And this is done through the use of GPU commands. As before, it was done through the use of writing to a memory address. Pika command lists are nothing more than a list of values describing patterns and data for writing to the GPU internal registers. So that's all there is to it. This is a white square. This is Mikage, a demo by DMP for Pika 200 that was presented at SIGGRAPH 2006, so they could show off their new GPU. It shows the impressive shadows, like you can see here, and fragment lighting functionality, like, for example, on the Samurai's helmet. And also, there is, you can't see it there, but the floor, the wood grain, was procedurally generated because the Pika 200 could procedurally generate textures. The name Mikage, that's where the Mikage 3DS emulator got its name from. And you may be wondering that, Citra got its name from the CTR, Mikage got it from this. Where did Panda get its name from? That is a really good question, so if you find the answer, do let me know. All right, my computer is lagging. Well, that's the joy of running it in a VM, so you could use PowerPoint. Would be quite nice if it would run live right now. Oh, this is awkward. Yeah.
It's fake. So yeah, basically turn it off and then on.
The whole thing? It's like frozen. Oh, it's back. All right, I'll restart the virtual machine just to be safe. Or maybe I won't. Let's see. Aha! No.
You're good on time still. So.
Okay, good. How do I send this? Aha! All right, sorry about that. Oh, now my first window is buggy. Okay, great. So this is a vertex shader in the Pika 200. The Pika 200 didn't use a high-level shading language like GLSL. Instead, shaders were usually written in assembly. So let me actually try to fix my thing. Oh, okay, I guess I can. There is uniforms at the top, just like in a GLSL shader, which is a read-only piece of data. In this case, it's our projection matrix. There's constants, output attributes and input attributes, so our position and our color that we want to output. And moving down to the main function here, it calculates 4 dot products to combine the projection metrics with our input coordinates and moves the output color. It doesn't do any modifications there. So we're quickly talking about the pixel pipeline. So in modern GPUs, fragment shaders are used which is a small program essentially to run the fragment pipeline. But in the Pika 200, there is no fragment shaders. And instead, it has a 6-stage color combiner to do so. So essentially, what would happen is vertex data would come from programmable shader units into the rasterizer. The rasterizer would generate a position, and then 4 textures would be sampled using these texture units. All of them could do 2D textures. The first one could also do cube maps, 3D textures, and the last one could also do procedural textures. And then this texture data and the vertex data would be passed to the color combiners along with lighting data. And color combiner is essentially what the name suggests, color combiner. It takes in 2 inputs and a way to operate between these 2 inputs and sort of produces a new color. So for example, you could have 2 textures that you want to combine, or you could have a texture and lighting source that you want to combine. And after that, after passing through all the 6 stages, you get a color which is then post-processed, and voila, you get the Kirby. Which, for example here, the beanstalk is mixed, the beanstalk texture, with the lighting from a light source. This is why it has like a sheen here. And then on the leaf Kirby standing on, there's a gradient from left to right. That's not probably how the texture was of the leaf. Instead, it was using a color combiner combining with horizontal position, so it gets darker as it goes to the right. Some showing off of the Pika, some games. So Captain Toad Treasure Tracker is known for being good and clever with lighting and shadow effects. The Legend of Zelda Ocarina of Time, which uses the fog rendering hardware that Pika has, and also ETC1, which is a format you probably never heard of, which is a compressed texture format. Mario and Luigi Paper Jam, it generates the seawater via procedurally generated textures. And Super Mario 3D Land does all sorts of things like stencil testing, logic operations, command lists that invoke other command lists, and more. And now we're talking about the digital signal processor. It is the same one that was used in the DSi, but in the 3DS it's used far more. And most games would ship with a common firmware, which includes support for 24 audio channels, ASC audio decoder for games like Pokemon X and Y and Fire Emblem, multiple audio encodings, effects such as reverb, delay, both mono and stereo input, but only stereo output. And the architecture for this digital signal processor might seem a little bit weird, but it's not really because, well, for example, it has 16-bit bytes instead of typical 8 bits. And that is because it is a digital signal processor and needs to process samples, which usually are 16 bits, but not always. It has some weird instructions that you may not find in a typical CPU, such as multiply add. It has support for tight loops, which is necessary for such work, and 500 kilobytes of memory. And this is a rendering of the DSP doing math, I guess. George added this, I don't know. And then there is some other miscellaneous hardware that we saw earlier. So the RAM, we went through that. There's also 6 and 10 megabytes of VRAM. One-time programmable memory for storage console unique keys, Wi-Fi controller, DMA engine, cryptography engine. You're probably not interested in all of that. There's 2 back cameras and a front camera, and an IR front LED, which is used in the new 3DS for face tracking, because actually the fake 3D effect would be quite straining. They would need this. All right, and we've reached the point to talk about the software stack, and we're going to start by talking about the Horizon OS. So the Horizon OS was the operating system of the 3DS, and it was split between the ARM11 syscore, which I actually skipped because my transition didn't work. So let me find the slide. I'm sorry about this. Oh, okay, I guess everything is broken now, huh? Okay, let's see here. Close this. Aha. Okay, quick interjection, sorry about that. I forgot to talk about the cores because of that broken effect before. In the original 3DS, there is two cores. One is the app core, one is the sys core. The app core runs usual line apps, including games and system apps. The sys core runs the operating system and services. We're going to see what those are in just a second. And the new 3DS has two more cores. One is for the head tracking service, which is for the straining effect that we talked about. And the other is just available as another app core. So they would have two cores. All right. After this quick interjection, I'm going to go back to the operating system, if I may. All right. So yeah, the ARM9 is for security and I/O, as we just saw earlier. So you need to get a firm grasp of firms. There is 4 in the 3DS. The one we're going to be talking about is the native firm, which runs 3DS games natively. This is the 3DS mode. In the ARM11, part of the operating system, the ARM11 runs the usual land and the majority of the operating system code, while the ARM9 is dedicated to cryptography and cartridge. There is the AGB firm for GBA games natively, and the ARM7 is the start of the SO, it runs all the game code. There is the Twilight firm for DS, pretty much the same. And then there is the Safe firm, which is a bare bones version of native firm for recovery, and you also can use it for updating. But later on, from now on actually, we're going to look at only the native firm here for when we talk about stuff. And the kernel inside the ARM11 is called kernel 11. I'm going to go through a brief introduction of what is a kernel. Every operating system has a kernel, which is considered the core of the operating system and handles various critical functionality. So in the 3DS ARM11, there is this kernel 11, and it is what we call a microkernel. A microkernel essentially tries to be as small as possible. It runs its services in user space, things that it needs to do, such as file systems and networking. It is less code, which means less vectors of attack. And it's generally considered to be more reliable. So if something crashes, not the whole thing crashes, like if your network crashes, the kernel doesn't. Examples are, this kernel 11, and also Minix, for example. And then there is a monolithic kernel. There's more types of kernels, but these are the major ones. In the monolithic kernel, all or most services run inside the kernel proper. And there's supposed to be fewer context switches, so everything's supposed to be faster inside the kernel. One example of a monolithic kernel is Linux. Kernel calls happen via the supervisor call, SVC, which is this. Here is an example of the assembly function called SVC. And like most operating system, kernel 11 is not a pure microkernel, but it is still a microkernel and handles memory management, process and thread management, and service and process intercommunication. Let's see what a service is. So service is, as we said, usual land processes. And inside the 3DS, they're managed by another service called the service manager. In order to interact with a service, say you're a game and you need to interact with them, first you need to get a handle to the service manager itself, which is a public service, unlike all others. And you do so using a supervisor call. And once you have a handle to the service manager, you can ask it for the handle to the service you actually want to use, say the file system service. And you do so using the send sync request. So you request the handle from the service manager through the send request. Then you need to set up a parameter buffer with a function you want to call to that service in the file system. Say the file system service, you want to call the read file function, which might not exist. And you pass the function being called and the necessary parameters. And then you need to send a request to the service, again using send sync request, and you receive an output buffer. The majority of communication with services is implemented with requests like this. Sometimes shared memory is used to reduce latency for some crucial services, such as the GPU service. And requests and responses are written in thread local storage, and as the name suggests, send sync request that is, they are synchronous, which means they're not async. The response is written after the function returns. But some services can queue something to happen later. So for example, there is this Y2R service, which is YUV to RGB color. Is typically used for decoding videos and FMVs and cutscenes. It doesn't stall until it's finished, which might take a while. Instead, it notifies you when it's done using a kernel event. These are some important services. So there's the file system, the DSP, the GSP for GPU communication, apt for applets, HID for input, etc. There's many, many. This is a function that asks the HID service to enable the gyroscope. It gets a thread command buffer. It makes a header to send in, and it sends a sync request. It checks if there's an error, and otherwise gets the result. All right, so there is then process 9, and process 9 is what runs inside the ARM9, and it is, unlike the kernel 11, it is a monolithic single process kernel. And all it handles, like we said, is cryptography and device I/O, talking to the cartridge, to the SD card, etc. It has overcomplicated C++ that reverse engineers hate, and it's really, really big. And here's a funny quote by PSI, creator of Corgi 3DS, goes, "If you ever feel useless, just know that process 9 calculates your SAHAs on the CPU despite having access to a full hardware SHA engine." All right, so this says live demos, but my system just broke, so I'm not going to do the live demos. I'm actually going to show you a video of the live demos. So here's a static frame. Here's a video, all right, of Panda3DS running on a Discord bot, and this is done through HTTP streaming. There is a server, and it sends the frames, and it becomes a GIF, and you can use the buttons to play at 2 frames per second. We've actually finished some games using this, so it's not as bad as it looks. This failed too, all right. Here is Lua scripting in Panda3DS. So you can use Lua scripts to create MGUI windows like this, and you can create a lag. Okay, there we go. You can create cheats and stuff. So you can, Panda3DS exposes these like functions such as write16, so you can write to address and stuff, and it also exposes events, so you can do a function every frame. So here I'm going to change, for example, the slider. If the video, okay, let's skip the video. Oh no, actually, here you can increment the rupee count, and there is also a button below that says, you can't see it, but it says murder link, and pretend I pressed it and link died. Oh, there you go. All right, let's get away from the videos. All right, so there is a hidden emulation talk inside this 3DS architecture talk. So first, before we get into it, I need to introduce you to HLE and LLE. So HLE stands for high-level emulation, and in high-level emulation, you essentially re-implement parts of the emulator system software in your own code to avoid emulating the hardware that is needed to run said software. So for example, I told you that the DSP has a common firmware that most games use. Well, instead of emulating the overcomplicated DSP, you can emulate this common firmware. The calls that would happen, you do so by re-implementing it in C++. The opposite of that is LLE, where you would emulate the entire DSP, which is, much harder, or actually may not be. And then you run the actual software, the DSP firmware, on that hardware. There is benefits to each side. So for example, LLE is slow because you emulate the entire hardware, but HLE is not easy. You need to reverse engineer the software you want to run, etc. We're going to look a bit more into that. So for the 3DS specifically, you can HLE the operating system, so kernels, services, process 9. There's more things that you can add HLE. And this is an example of something being HLE'd. So there is the file system service. And this is an HLE implementation of the file system service that returns if an SD card is inserted. And if you were to LLE this, you would need to emulate the complex SD hardware interface. So, there are some benefits to HLEing, of course. So just a quick summary. LLE is tedious because there's much hardware to implement, especially in the 3DS, and it's also slower. But beneficially, you can run any 3DS software, including bare metal firmware, such as Linux for 3DS or Godmode 9. HLE is again tedious because there's so many services to implement, but it is performant, but still error-prone, and there's many things to reverse engineer. There's also a hybrid approach you can do, so you can HLE the kernels, but you could LLE most operating system services. And what does LLEing services mean? Well, services, as we said, are usual end apps, so you can literally just take the binary and just run it. That would be LLEing it in your emulated hardware. You run it. This is a nice bit of balance. It minimizes work, improves performance and accuracy. maintains accuracy. So as a 3DS emudev, you need to consider how you're going to approach the CPU. And there's many ways to do so. First, let's take a look at an interpreter. So an interpreter, you essentially interpret all the opcodes that you need to run, which is to say you switch through them, you decode them. This is slow, but it's also very portable. As long as your code compiles to the target platform, you're pretty much good to go, usually. And this might be your choice because a GIT might be very hard or impossible on whatever you're targeting, say an iPhone, I don't know, or WASM. GIT recompilation is converting the ARM code to host CPU code. So if you're running on an x64, you would convert the ARM32 code to x64. This is the most common solution. It's also easier if you use dynamic, like Citroen Panda do, which can perform ARM32 to x86 or ARM64. So you can run on most devices that most people might care about, such as computers and phones and stuff like that. Then you could also consider virtualization. As far as I know, this hasn't been tried yet in the 3DS, but there is an ongoing pull request to try to do this. So virtualization is the way apps like VMware and VirtualBox work. And on some ARM32 and some ARM64 devices, there is the possibility to execute 3DS code natively through the use of virtualization. It's not possible on all ARM64 devices because they're removing this functionality, unfortunately. But on some Raspberry Pis, for example, on some rooted Android phones, you can run 3DS code natively implementing this. We don't yet know if it's faster than GIT, but yeah. And then you could also consider ahead of time recompilation, potentially. So that would mean recompiling the ARM code from the code section to your host operating system. This has a benefit compared to the GIT, which is that if you ahead of time compile, you don't need to compile fast, which means that you can perform optimizations. So for example, you could use something like LLVM to produce optimal code. So yeah, this is another potential way you could run your games. Then you need to consider how you're going to approach the GPU. Again, there is two ways to go about it. So you could do software rendering, which is simpler, but again portable and slower. That's the downside. You could also do a hardware renderer, which draws on the GPU using something like OpenGL, Vulkan, Metal, etc., DirectX. This is much faster and obviously ideal for playing games, but less portable. So for software renderers, how do you make them faster? That's what you got to consider. Well, there's many ways to make them faster. For example, there's multi-threading. You can draw on concurrently on several threads. And then you could also use a recompiler for a software renderer. So you would take the Pika state, the current render state, you would make a small binary for it, and you would run it for said state for every pixel. So this would avoid like running a branch for everything. For example, if the depth buffer is disabled and you don't want to check for every pixel. This is optimized, and you can also reuse this compiled binary if the same rendering state arises again. This is something that, for example, PCSX2 does for its software renderer. And then for hardware rendering, well, it's challenging. You have to make sure you choose the ideal API, manage surfaces correctly, such as textures, color buffers, etc. There's many other problems to solve. For example, dealing with the parts that aren't really OpenGL compliant, or games that use depth buffers as color buffers and write to them directly. Or yeah, there's many. For example, tracking when a texture has changed and it's no longer valid. There's many issues to solve in a hardware renderer, which makes it a bit harder. Then you're going to consider how you're going to approach the Pika shaders. So again, you can do an interpreter that's simple and also too slow. You could do a GIT on the CPU. So this is the vertex shader we saw before, and it is converted to some scary-looking x64 assembly, although most x64 assembly is scary-looking. And then another approach, this is decent performance, but it could be better, is to recompile these shaders from this state to your own GPU, so something like GLSL or SPIR-V, for example. This would give even better performance, but it might not be possible for some select Pika shaders. So yeah, let's move on. Then you need to consider how you're going to emulate the picapixel pipeline. There's a lot of things to emulate in the 3DS. So one approach is specialized shaders. I think this is what Citra does. So essentially, you compile a specialized shader for each picapixel pipeline configuration. That's how you will emulate the picapixel pipeline and run it on your GPU. This has low GPU usage because those specialized shaders are specialized and small. But lots of time is spent compiling shaders, which causes stutters on some games. This is the most common approach. Panda3DS currently doesn't have this, but it has Uber shaders, which is a term coined by Dolphin, which aims to solve that issue of specialized shaders of causing stutters. You essentially take an entire emulator for the picapixel pipeline and run it inside a GPU fragment shader. So you don't need to compile many times, you just compile once and you run it forever. This, however, has higher GPU usage because it's very, very big, but no compilation stutter. And it works well on modern PC GPUs, but struggles on mobile GPUs, for example, or lower end ones maybe, because it's very big. And this is what Panda3DS does. But however, an even better solution would be to do hybrid emulation. So you will compile the specialized shaders asynchronously in the background, which you couldn't do before because you need them to render. And while they're compiling on a different thread, you use the Uber shader right here, which is, this is used for every call until the relevant shader is ready. And this gives, I think, better performance than either method and works well on all GPUs. And this is what Panda3DS wishes to achieve after we're done with specialized shaders. And finally, there is the audio DSP. There's two approaches, as we saw earlier. There is the LLE approach. So in the LLE, you need to consider how do you optimize it. Do you recompile the firmware to your own architecture, or do you do it ahead of time? Teatro comes to mind, which is an emulator, assembler, disassembler for the TEAC DSP, and it's used in Citra and MounDS. And you could also, instead, HLE DSP, which should be faster, and things you need to do with that is improving the current DSP reverse engineering efforts. It hasn't been fully reverse engineered. You would need to make test ROMs and tooling, and then you would need to optimize it. You could do so using SIMD or SIMD and multi-threading and. That is all for emulation. And now I'll show you again some ways we are exploring new territory in the 3DS emulation to sort of wrap up this talk. So Panda3DS comes with Lua scripting, including a text editor, so developers can make scripts and mods and tests and stuff like that. And we also have MUI support. You can have your little windows, and I think it's pretty cool. Also, Panda3DS here is running CTR aging, a factory test program some other emulators may struggle with. And Panda3DS running on the Wii via the same HTTP streaming, not natively on the Wii. Yeah, unfortunately. Not natively on the Wii, just using HTTP streaming. We thought to show it off because, we have an HTTP server, just throw it on the Wii, whatever. And the physics book there, the monitor rest. I failed that class. All right. We have a revolutionary UI. It has panda icons. And you can play on Discord with all your friends. That is it for me. Thank you very much.
Hello. Test. Does it work? Yeah. Okay. Thanks, Paris, for a nice talk. Anybody has any questions? We have quite some time. I'll start here.
Hello.
Hello.
Great talk. How much time did it take to build all that stuff?
Well, I think we've been working on it since the FOSDEM applications opened, since we got accepted, actually. So I would say 3 months now? Something like that. Yeah. The original version was not nice, but we fixed it. So yeah.
Are you thinking about the presentation or the emulation?
Not the emulator, not the presentation.
Oh, I'm sorry. Silly me. Panda3.
3 months.
3 months. Yeah, we built all this and the presentation. All right. No, it has been in development since September 2022. Yeah, so more than 3 months. 1.5 years now.
Who else had a question? Sorry. Hello.
I have a question regarding GPU emulation.
Yes.
Have you considered using parts of Mesa, for example, which has a lot of GPU stacks, OpenGL implementations, and can do compilation to native GPUs? I wonder if it has been explored, not necessarily in Panda3DS, but any emulator.
That is a good question. No, I haven't considered it. I don't know if George has. He's the main developer on the Panda3DS. You can ask him directly if he has, but as far as I know, no.
Hey, thanks for the presentation.
Hello.
I was curious, like, do you know how, you mentioned that, like, in the 3DS, the different generations of the hardware have more hardware? How do games and other software handle that?
The different generations of the 3DS have more hardware?
Yeah, and the different CPU speeds and whatever, do the games do more if they are on different versions of the 3DS?
Are you talking about the DS or GBA backwards compatibility, or are you talking about 3DS games? Because the 3DS in all generations has the same CPUs, but the ARM11 has more cores.
Yeah, but what do they do with the more cores?
Oh, I think I mentioned it, but I'll show you again here. Yeah, so one is used for running games, one is used for the operating system. This is used for head tracking, so your eyes don't get dizzy from the 3D effect on the new 3DS. These two are on the new 3DS. And then the new one, this one is available as another app core. I think for backwards compatibility, if you try to run an older game on the new 3DS, it tries to run it on, it tries to downclock the speeds and not use the extra app core. And if you run a new 3DS game, it uses both of these to run the game.
Okay, thank you.
What happens if you run a new game or an older generation of 3DS? Does it fall back and turns off parts of the game not to crashing because there's no CPU?
I'm not. Yes. They asked what happens if you run a new 3DS game on all 3DS, and I'm not sure, but my guess would be that it would display some sort of message that you can't run it on this console. This is what happened, for example, when trying to run a Game Boy Color game on a Game Boy if there was no such support. So I would assume that's what would happen, but I'm not sure.
I'm wondering about the ARM7 core. You mentioned it was disabled on the 3DS mode, but
yes.
Can it be used in certain situations, like running Virtual Console GBA games? Can it be used to run natively, or is it still emulation?
Did you ask if it's used to run natively Game Boy Advance games?
Yes.
Yeah, that is its only purpose, and also to run DS games, because the DS also had an ARM7 core. The ARM7 only exists in the 3DS to run Nintendo DS and DSi games and Game Boy Advance games natively.
For the GPU emulation, did you consider using compute shaders on modern GPUs as well? Like speed up parts of the rendering pipeline that are hard to do with normal fragment and vertex shaders?
Yeah, that is a question for George, but I think he definitely would have considered to use computer shaders, yes.
Does anybody else have a question?
My question was, you said that currently Panda3DS supports Windows, Linux, macOS, and Android. And do you expect to support more platforms in the future, like WASM or iOS or?
I personally wanted to try at least to port it to WASM. It would. It's not that easy. There's no recompiler from ARM32 to WASM. You would need to use an interpreter. Currently, Panda3DS doesn't have one, but we're hoping to add one eventually. And then there is WebGL, which is not great, but you can use it. Theoretically, it should be possible for WASM, but it's in the future plans. What was your other system question?
iOS.
iOS, I think iOS also has some problems with running a recompiler. It needs special privileges. And also there's the fact that you can't really post an emulator on the App Store, which is unfortunate. But we definitely want to at some point, yes.
That might change in the future. I may be able to.
Yeah, hopefully.
I have a question. I'm allowed to ask a question. So it's not really a question, but George is in the chat and he's answering some of the questions. I'm not sure if you have access to the chat. You can read the answers. If
The FOSDEM chat?
Yeah, it's on Matrix.
No,
right.
This computer is not connected to the internet, for one.
It's secure, ultra secure, but
Yeah.
But yeah, okay. But the answers are too long to read for now, so just check Matrix for now. So my question is, it's actually related to Anis's talk because he mentioned vertical slicing. I'm very curious, how would you do vertical slicing for complex systems such as this or Nintendo 64, for example, right?
Could you provide a definition for vertical slicing?
Like very... Anis, could you provide a definition for vertical slicing?
I don't think it would be good. Definition, like you emulate just...
Like you emulate just the necessary path to emulate, let's say, the start of a game and then go on from that. Or, Hello World, or just maybe, I don't know, a test run and then test game and then more stuff as you go.
So sort of test-driven development, or?
More like emulating as little as possible, but just having feedback, visual feedback from the...
I don't know if that's possible, emulating as little as possible. Even the simplest ROMs use quite a bit of the operating system. Even like a simple triangle uses quite a bit. So yeah, I don't know if it's possible, if I understand the definition correctly.
Thank you.
So, first question, how do you feel knowing that every second spent on emulation is making a Nintendo business executive cry? And secondly, do you think ahead of time compilation could like seriously improve performance, especially in lower end hardware, or do you think like the issue lies more on the GPU on the rendering side?
Yeah, it definitely could. I don't know if it has been tried yet, but we do want to explore that possibility. The big thing about ahead of time is, well, the thing about the 3DS is that it doesn't really do a lot of any dynamic code execution, so it should be theoretically possible. There is CROs in the 3DS, which is the alternative of DLLs in 3DS, but George has told me that they can be handled. And yeah, the big thing about AOT, yeah, that's all he told me, he didn't elaborate. But the big thing about AOT is that you can optimize the code, so I would think that it would run quite faster. But we don't know.
Okay, I think this is the last one.
How do you deal with the system applets that the 3DS has? Do any games even interact with those in any way?
When you say the system applets, do you mean like the home menu, stuff like that?
Yeah, like when you go to the home menu, there's the little apps at the top, for instance. How do games interact with that? Can they launch other games, that kind of stuff?
Games in the 3DS only interact with services. They don't interact with the system apps.
Okay, final one.
Yeah, you talked a bit about the new 3DS infrastructure and the additional CPUs. And I was wondering, when you run like older games that weren't using the additional CPU, does the new 3DS automatically use the additional CPUs, or are they just completely ignored and just unused?
No, as far as I know, it just uses the original app core, the one it has, and it also downclocks it to the original speeds.
Oh, wow. Thank you.
Okay, great. Let's thank our speaker again.
Thank you.